first, and don't touch those two buttons.
Okay. Hello, everyone. Thank you very much for the invitation here in NANOG. I can say that it's my first time. Now, introducing my name, I remembered a funny story. I came here in Washington on Sunday, and after walking around for some time, finally managed to reach my hotel. I get in and I went to reception, and hello, my name is George Nomikos. And suddenly the man behind the reception changed his behavior and asking, who are you, what are you doing here, why are you here, something like that. And afterwards I realized that saying my name, George Nomikos, he understood that my name is Nomighost. Anyway, let's go. I will present a recent work conducted with Xenofontas Dimitropoulos in Fourth. There I'm a research engineer, and Fourth is a research foundation in Greece, in numbers about 1,000 people there. And it's about a tool on how to detect IXPs in traceroute paths. And the name of this tool is traIXroute. No. Okay. Let me ask you something. How many of you use Traceroute? Please raise your hand. Awesome. Let me ask you something else. Why it is important to know if traceroute paths cross an IXP? Or why it is important to know, in general, if our traffic goes through an internet exchange point? A potential answer to that question is that maybe it offers much more transparency over where our packets go. Might be considered quite useful for networking administrators to troubleshoot end-to-end paths, or even for researchers to better understand how the IXP ecosystem evolves. Unfortunately, based on the literature, we cannot be pretty sure that we have crossed an IXP, stumbling on an IXP IP in the traceroute path and having as information in our hands only IXP prefixes. And this could happen due to different reasons. For instance, due to third-party IPs. For instance, assume here that we have an example of a layer 2 IXP topology with two IXP members in the borders, and the traceroute path, as you notice, with a dotted line that crosses the border router B. If this border router B replies with a third-party IP that belongs to the IXP subnet, then it's possible to falsely infer that we have crossed the IXP fabric, but in fact we didn't, as you can notice with a dashed line. Some other reasons might be inaccuracies in the IXP prefix data, and what about if these prefixes are used in other operational subnets? So, in this work, we propose a new tool, traIXroute, on how to detect and identify if and at which hops in the traceroute path we have crossed an internet exchange point. We deployed this tool in Python 3. Of course, it's open source, so everyone can contribute. It's licensed under GPL version 3. And we announced the first release in May last year, directly after our publication in PAM conference. And the good news, last week we also announced the last version of the tool. What are the key features of traIXroute? traIXroute is a general purpose tool in which we can detect there with that tool the crossing links on the fly. This means that we don't need a bunch of traceroute paths in order to infer with high confidence this crossing, but only with one traceroute path we could have this result. And this fact also allow us to have fast IXP detection. We tried to focus only on easily accessible IXP data, and this is something that allows us to overcome some of the existing shortcomings. Also, traIXroute supports direct communication with the RIPE Atlas infrastructure. This means that through the tool, you can create or even fetch measurements from the RIPE Atlas database in order to analyze them and then to see where you have an IXP crossing or possible IXP crossing in traceroute paths. Most importantly, in the last major revision of our tool, we also added a new functionality. Actually, traIXroute supports remote peering identification. This means that after we have detected an IXP crossing, we can also infer if the near-end IXP member is also a remote peer. This functionality is mainly based on data from a new tool, the name of which is Remote Peering Jedi tool. This tool actually initially emerged and finally deployed during IXP hackathon in the last RIPE meeting, and in that tool also some of our colleagues are also involved. And the capability of this tool is to detect and geolocate the remote peerings in the IXPs. Finally, we followed the modular design, and this is something that allows us to easily extend the tool with new IXP detection capabilities. And of course, it offers flexibilities to the users to configure the tool based on their needs. As I said before, we follow the modular design. Here you can see the 4 main modules. In the first module, we have the initialization of the tool with some input data. In the second, we try to receive an IP path sending a probe. In the third module, which is the most important module for us, we have deployed our methodology in order to take the big decision where and if we have an IXP crossing. And finally, in the fourth module, we try to formulate all the output of the tool. So in the first module, as I said, we have the initialization with some input data. For this reason, we used 3 kinds of data sets, IXP membership data and IXP prefixes provided by provided by PeeringDB and Packet Clearing House. And as a third data set, we used prefix to AES mappings provided by KDA based on route use BGP dumps. At this point, it's worth mentioning that the first dataset was the most important dataset for us for 2 reasons. Firstly, because it offers fine granular information that associates IXP IPs to IXP members, and secondly, never used from previous works for this purpose. As a result, we try to validate the accuracy of this data. To remember, PeeringDB is a database with self-reported data from IXPs and ISPs too. And Packet Clearing House is another database that contains information, of course, IXP related. And it retrieves all this data from BGP dumps, from route collectors located into IXPs. So we also used these BGP dumps, and we managed to validate the accuracy of the 93% of the IXP membership data from PeeringDB and the 92% from Packet Clearing House, respectively. Now, in the second module, of course, is a simple module. We try to receive an IP path, sending a probe for a selected destination, IP destination, or a URL, or whatever. And to do that, we can use either the well-known traceroute or Scamper. Scamper is another more sophisticated tool provided by KDA, implements Paris traceroute, so this allows us to overcome some anomalies in the path due to load balancing. And now, in the third module, in which we have deployed our methodology, you notice that it consists of 3 main steps. So, to better understand how all this process and works, let's see some more details for each step. Particularly, in the first step, we try to find an IXP IP in the path based on IXP membership and prefixes data. And how we do that? Assume that we have a sample of a traceroute path from the second module. And the first thing that we have to do here is to use a sliding window, hop window, of size 2 or 3 IPs. Let's say, for our example, that we have set it to size of 3. Now, for each hop window, we apply our methodology. We check for IXP crossings. We slide the window. Again, we reapply methodology. We infer our result, and so on. So assume again that we have a sample of a hop window of the traceroute path. So the first thing that we have to do here is to check if the middle IP is an IXP IP. And how we do that? We check if this IP is included in the IXP membership data or belongs to an IXP prefix. Let's say that we have a hit for our example. Now, in the second step, we translate the IP path to an AES path, and then we check if the AESs adjacent to the IXP IP are also members to that IXP. Having this hop window from the previous step, we map the border IPs to AES numbers based on prefix to AES mappings, and then we check if these AESs are members to the candidate IXP that we have in the middle, using the IXP membership data. And now, in the third step, we take the final decision, gathering all the information from the previous steps. We are ready to say if and at which hop in the traceroute path we have this IXP crossing. Of course, taking into account our methodology, you noticed that to infer these crossing links, we have to do 2 main things. The first thing is to check what information we have and also what requirements are satisfied. So, for this reason, we formulated various IXP detection rules, and we split them into 2 groups, in strong and weak evidence rules. To better understand what are about these rules, let's see some examples. Consider again that we have a sample of a hop window with an IXP IP in the middle. So a strong evidence rule requires AES information for all the 3 IPs, and especially for the middle one based on IXP membership data. And if the border AESs are members to the IXP, with the first 2 AES numbers to be different, we can say that this rule is satisfied, and then we infer that we have crossed an IXP in the first hop of the hop window. I mean, in other words, before the IXP IP. A weak evidence rule does not require AES information for all the 3 IPs. And also for the third one, not to be member to the IXP. Again, if this rule is satisfied, we can say that we have crossed the IXP. But of course, now we claim this result with lower evidence. And now, in the fourth module, collecting all the information from the previous steps and modules, we try to formulate, and of course, after the path analysis, we try to formulate the output of the tool. And running this, as an example, this traceroute command and enabling some arguments, the first thing that the tool can print is a short dialogue about what information we keep in our database in order to make all the path analysis. And then we print the candidate traceroute path, augmented with some AS-based information, with some detected IXP IPs. But most importantly, at the bottom, we have all the IXP crossing links and, of course, the inferred remote peering links for the detected IXP for the candidate traceroute path. Now, as a next step, we try to see what else we can learn from IXPs and traceroute paths. And for this reason, we used 30 million probes provided by CADA, and we applied onto this path 16 various different IXP detection rules. And our results show that in about 20% of these paths we have IXP crossings. We don't see usually more than one IXP crossing link, and these IXP crossing links happen on average at the middle of the paths. So to wrap up, traIXroute is a tool to detect and identify if and at which hop we have IXP crossing links in traceroute paths. We offer fast and on-the-fly IXP detection. traIXroute supports remote peering identification and direct communication with the RIPE Atlas database. And at this point, it's worth mentioning that traIXroute also supports a generic traceroute path format. This means that you can import every path from every database after a proper conversion in order to analyze it. And then we hope to offer a better level of transparency and a more effective way to troubleshoot end-to-end paths. So for this reason, for these reasons actually, we hope this tool to be useful in the networking community. Now, as a future work, we still plan to support IPv6. We need further ground truth information to validate this tool. And of course, we plan to include additional information from other databases and to integrate some more mechanisms in order to offer a better level of accuracy and, of course, more functionalities to the users. So this is traIXroute, a work funded by the ERC Netvolution project. Thanks a lot. Thank you very much.